Hello, welcome. This is my newfound passion and it's about PV systems. I did a training on it and now I have to mm, put my contribution for those who would actually benefit from it. I expect the world over, the technicians and the PV system designers, whether for small PV systems or for large PV systems. I hope you get something out of this. And I'll do it in the form of a picture format, and I'll be describing what I did to this system. Right. This is the place where the installation was done. It was done by a company, but the, the customer was looking for a solution because the installation did not perform to expectation. This is a small shop and it's an off-grid PV system. Right, on top here is the module mounting, and then inside here you have two fridges basically, but there are two other lights. Energy saving they are. You will not consider them that much because they don't take much power. Outside there are two lights. You see this one and the other one here. Here is a shop that actually sells drinks. The basic load that we have to consider is the two fridges. I will show you the sizes and the specifications of the fridges. And we go through and show each other what was the problem and then how I solved the problem. Right. So it's an off-grid system. The lady, the owner of the shop, decided that she powers everything using solar power. The shop basically runs from morning around 8, 9 in the morning up to 7, 8 there in the evening. They don't worry much about the evening anyway, but they would prefer that the system be running on just for powering the lights and another fridge if possible. Now this is the site, and maybe you can see it from a distance now, but you have the modules on top there. There are 3 sets of 2 modules, and I can actually say that these modules were all connected in parallel. Anyway, that will be the reason why we have to discuss about it. Right. Here's the shop off-grid system. That's modules, charge controller, batteries, and then inverter. Right. Now, where this location, where this shop is actually here in Namibia. This is Africa, and this is the GIS solar map. You can actually tell that Namibia is one of the best solar installation compared to other parts of Africa. Here in the Sahara, of course, there is also good solar installation, but in Southern Africa, you can see that Namibia has the best, and it's basically the only one, except part of the southern Angola and part of northern South Africa. So Namibia borders Angola, Botswana, part of Zambia, and South Africa. Now, here is where this system was installed in Namibia. Let me zoom it a bit and show it. Yeah, that's where Namibia is, and that's where Windhoek is. So it's installed in an area where there is good solar installation. And So this is the map of the solar installation for Africa, case of Solar GIS. Right, to go next and show the next video. Right, this is what the customer has. This is the biggest load that she has, and this was problematic. We advised the customer to actually change this freezer to a more energy efficient one. But the advantage of this freezer is it has glass windows. For marketing purposes is good because the customer can see from outside, because this is a tuck shop. So it has glass at the front, so you can see it. But look at the power consumption here, 8.83 kilowatt hours per day. That's a lot. That's not solar system friendly. I don't like it. So this is where we concentrate on the power consumption, and then maybe the powering of it. But well, you can see 3 times when it's running 3 amps plus minus times 2, that's about 600 watts, or 700 watts actually. 700 watts when it's running. It runs and stops, runs and stops, something like that. So this is the consumption that you actually have specifying, and it is rated this way. This is the rating for that fridge. It is rated B. It's classified in the B region, so that's not energy efficient at all. And the kilowatt hour per year, you can actually calculate it, although it was not legible enough, but I could actually see it a bit closer. That's 2,474.7 kilowatt hour per year. Well, you can calculate it and guess maybe in the worst case scenario, but you factor in the winter time and other factors that, well, it will not reach that specification of 8.83 kilowatt hour per day times 365, which is days in a year. That would be 3,222.5. So it's less for a year, because there is the winter issues and the other issues that actually come with it. Right, now come back. Now here is another fridge, the AEG fridge, and this fridge is well suited for a solar system. You can actually check the volume and whatever the specifications for it. But here's the power. Look at it, less than an amp when running. It takes less than an amp when running. That's about 200 watts, 230 watts. Yeah, 200 watts in fridge. It's an AEG. It was a deep freezer. This is a deep freeze. The other one is a standing freeze with the windows, with the glass windows, where you can actually see the drinks. So this fridge is rated A++, which is best, one of the best. Okay, the best will be 3 pluses. But look at the power consumption, 225 compared to 2,400. That's 10 times less kilowatt hours per annum per year. That's 10 times less. So this fridge was best. So, well, the customer didn't like it because this is a deep freeze. Plus, well, people don't see what we have when they come. They want the drinks. They cannot choose. They normally would want to choose from what they see. So, well, but for an off-grid system, this is the best. Right. Now we go to what this customer actually bought the systems that were installed. This is the Yingli solar module, one of them that was installed, and you can see the specifications of it. We look at the rated power, which is the watts peak. That's 265 watt peak, and the rated voltage was 30.5 volt peak, the rated current 8.7 amps, and then the open circuit voltage 37.8 volts. Yeah, okay. So this is a much more of a grid-tied system kind of module, but here's the specifications that you must consider. Right, the installation that was done was all 6 modules parallel connection. That was a parallel connection, so you can actually check the solar generator was giving you 1590 watts, and that was also will be giving you 52.2 amps, and maximum open circuit voltage for that kind of connection will give you 37.8 volts, and the peak maximum voltage will be 30 volts. That is the voltage of each module. So, but then you'll see that was a problem, because you wouldn't get that much power and no current that much would actually flow because of the other components that we used. So what I did was to do this same power but less current, and of course connecting modules of open circuit voltage, that much will give you that much open circuit voltage, and the maximum power will be double because it's 2 modules in series. That will be double the voltage, of course same current, and 3 sets of that will actually give you that much current. Okay, now we go next. Now this is the inverter that was given to the customer. This is where the problem was basically. The inverter part was okay because it would actually carry the load. It was capable of carrying that load, 3 kilowatt, although I doubt you normally would have a power factor of 0.8 or so, but these people are claiming that this inverter is a power factor of 1, but well, I would give it 2.5 kilowatts. But anyway, that area was okay, it was sized proper, but the problem was here on the solar charger mode. Look at the power rating, the maximum power that this inverter can actually, the charge controller, the solar charging part would actually do is 600 watts, and well, with 24 volts, the maximum open circuit voltage 75 volts. So what was the problem? The inverter is actually having a charge controller inside it. Both inverter and charge controller inside, and also a utility charger, a battery charger using commercial power or grid power. But this is an off-grid power system, so we don't talk about that. So you have a inverter that is okay, yeah, but the charge controller was a problem. So you can see 600 watts maximum for the charge controller inside the inverter, and maximum open circuit voltage is 75 volts. So what will be the problem here? You have that much power coming to the inverter, to the charge controller, and would actually give that much current. Maximum open voltage will be okay for the charge controller, but maximum peak voltage would be 30.5 volts. But now you have a 24 volt system and you want to charge it 30 volts. That's a problem, because a 24 volt battery would actually get to 29 something volts. So you have a problem there. And also you have a 600 watts maximum charge controller, and you have that much power from the generator. So that's 1000 watts going into the air. So This is what was supposed to be done, but this would actually not work also with the same charge controller. It will not actually work with the all these settings would not really work with the charge controller in the inverter. So how would we solve that? Would solve it. Okay, we'll show you next on the next clips. Right, this is just basically the same information. This is, you can see that the charge controller in the inverter is actually in maximum power point in MPPT charge controller. Range of that much 30 to 66 for DC. Right, but rated power max 600 watt. Our inverter is a 3 kV a 24 volt system inverter. So that was the model that was given to the customer. But the inverter side is okay, the charge controller side was a problem. Right. Now the battery is okay according to what I've seen. It's a 200 ampere hour battery at a 20-hour rate. It's a 12 volt. That's 6 of them. 1, 2, 3, 4, 5, 6 batteries. So you have 24 volts. This 24 volts, 24 volts. So 3 sets connected in parallel. That will be 200 ampere hour battery, another 200 ampere hour battery, another 200 ampere hour battery. That's a 600 ampere hour battery at 24 volt. So, well, according to my calculation, well, it was sized well according to calculation and the usage of the customer, the expectation, but it was okay. Right, here's where the problem was from the indication of the inverter. Well, I can say the inverter was a Mesa inverter. I can show you the model on the. You can check the model on the site nameplate of the inverter. Right, you can see from the information here. This is when the solar module was connected, as before I changed anything. So it was using the inside charge controller. And now you can see this is the battery from the PV to the battery. The current that is going into the battery, that's 0 from the PV, 0 current, so it's not charging at all. Right, the battery is not being charged. Right, next you can see at one other time, now the battery is charged but at 4 amp. So charging a 600 ampere hour battery at 4 amp, you can imagine how many hours you need to charge the battery. You only have 6 hours a day, normally on a very good day. So well, you'll see how much energy that the load was taking from the system. 4 amps was nothing. Right, now we go on. This is where you actually start to see a problem. The battery was actually giving out 9 amps, and you see the voltage here, 24.6 volt. This battery is actually discharging. This is a battery that is discharging. Right, here it shows it's charging, but well, it is trying to charge, but you're actually having a battery that is giving out power rather than giving in power, getting power from the module. Right, and then next you can see the voltage, that's 26 volt, the battery voltage, sorry, 26 volt from the PV generator, which means you basically can't really charge a battery of 24 volts with a 26 volt PV system. This was a problem because the PV modules were connected in parallel and their maximum voltage, the peak voltage was 30.5 volts, remember. So you have a problem. That's a problem. Right. Then next, this was just a confirmation to check whether the display of the inverter is giving me correct 26 volt, and my meter was also showing 26.8. Well, that's more difference, no problem. Now you see how much the load is taking. 433 watts. The load is demanding 433 watts, and that is the battery voltage. And the PV is providing 328 watts. So you're actually having power coming out of the battery. You need 433 watts, but you are getting 328 watts from the PV. So you have a deficiency there. There's no energy supply. Right. Now, at one time, well, that was a very good day. You would actually get 623 watts from the PV, and 623 watts was the maximum you can ever get. Well, the charge controller of the inverter was rated at 600 watts, remember, so you won't exceed this. This is when you would have a charging current. Remember, there was a time when you had 4 amps charging into the battery, but most of the time the battery was discharging. So the customer complaint was they cannot run the fridge much longer. If they run the fridge even during the day when the sun is okay, you start to have the inverter complaining that the battery is now low. So the battery was discharged. So they would manage the big inverter. Remember that glass window in the fridge. They have to manage the fridge, switch it on, switch it off, switch it on. So they started having problems. So now this is what I did. Right, this is the inverter, the Mesa inverter. Remember the nameplate here. This is what I did. I had to advise the customer to buy an external charge controller, and that charge controller had to be an MPPT charge controller, where you can actually have an input which is more than 75 well, the 37.8 volts times 2, and it had to be able to handle the current. Remember how much current we needed from the calculation. Yes, the current we needed from the calculation. Our charge controller was supposed to be able to handle a current of 26.1 amps, maximum open voltage 75.6 volts, and be able to handle 1590 watts at 24 volts, of course. Right, that was the specification that we needed. So now this is the inverter and the charge controller. Now external charge controller. The customer, I gave the customer 3 options, and the customer had to settle for a 70 amp and 150 volt input charge controller from Victron. There were others which were even of the same brand, which was I think 85 amp, 75 amp, but I don't remember really, but also 100 amp, but because of the price and all that considerations, she settled for that, and I said okay, I think this would work, and this was the charge controller installed now. It had 2 input PV MPPT inputs, and then output battery charging. And, well, you can check for the datasheet on the net for the charge controller. Then maximum power point tracker, and these are the specifications general on the charge controller. Now this is the improvement. Now you can see now that the battery was charging now to 25.7 volts, and the load actually is now 24 amps from the battery. So you have 25 volts, 24 amps. The battery is at 25 volts and the battery is giving out 24 amps. Check here, there is no solar module anymore because the solar generator is not coming through the inverter anymore. So it's just battery output, because that's what it is doing. The inverter system is only seeing the battery and the load that is connected to it. So 25 volts, it could hold 25 volt, 25.7 volts, it giving out 24 amps, and at that voltage, that was the load power. And you can imagine that the charge controller of the inverter was rated maximum 600 watts, so we only had 100 watts left on that one, 513 watts for the load, and it could hold 25.7 volts. So that was a great improvement, and even more, you can see that now the battery was actually charging, giving out that much power, charging 23 amp from 25 to 27. That's an improvement, and same power actually, 27 volts charging. At one time it would actually go into float. So that was an improvement after putting an external charge controller. So this was the installation. You can check, this is the place. Well, I sometimes like photography as life happening elsewhere, and I was on top of that roof, and I could see, well, the panels are very dusty and dirty, which I later cleaned up, but this is how they were arranged. The tilt in window basically should be around 30 degrees facing north. They were facing north, of course, but a bit tilted up. So right, now so we have, well, somebody there checking on the solar modules, and you can see the dirt on the solar modules. I can zoom it a bit. You can see that they are very dusty now, like very dusty. And even those ones, if I zoom them, you can see that they are very dusty. Not yet very dusty, because it was almost plus minus a new installation. Right now, that heat, of course, because the sun in Namibia is very hot, and yeah, gets very hot. Need a sun heat. Now, after some service, this was the cleanup of the solar modules. There's a cleanup there now, and also you can check here, cleanup also. Now a bit better, but they still needed some polishing up here, of course, but there was now clean of the dust. Right, back to the first photo. Beautiful sign, beautiful sky, always shining in Namibia. Very good solar resource in that country. Thank you very much. Remember, you can contact me on taramirimi@gmail.com. You can check on my YouTube channel videos, and you can have a comment, you can improve, you can suggest, and you can critique, but well, I hope this would actually help someone who would have a similar problem. This was basically a design problem, and it was a slight error and an overlook on the installation. The main problem was, well, one, the parallel the modules instead of making a series connection, and the charge controller inside the inverter was smaller than the solar generator. So that was the basic problem of the installation. after what I did, the customer well appreciated it, and can actually say, well, I was given a token of appreciation. So thank you. I hope you enjoy, and check on my next video. We'll be doing the charge controller, do it yourself, using an embedded system. Have a great life. Goodbye.